Hello once again. Today we will have our new topic about impedance and admittances, but this is under the topic of series parallel, RL, RC, or even RLC circuits. But before we proceed to those to the discussion proper, so thank you for subscribing on my channel again, and as of the moment we have 510 subscribers. Thank you very much. And to those who are new, you can hit the like button, share it with your friends, and subscribe on this channel for additional information, so that you can have a notification bell that there is a new upload or a new video that I will share to the review community. And as well as this is if you want to have a question on what I am discussing here and from the previous lessons, you can comment on the comment box section of the video, so that I can give insights and answer your queries. Okay, let's move forward to this discussion. Before you go to series, parallel, RL, and RC series circuit, you need to understand first what is impedance and admittance. Okay, now admittance and impedance, or impedance and admittance, are it's like the same with resistance and conductance. But however, in the AC, we're considering now the frequency domain. So all of the parameters are already present in terms of the frequency domain. So you already have resistance, you already have an inductance, L is inductance, and C is capacitance. Okay, in terms of inductor and capacitor. Okay, so let us discuss first what is impedance. Okay, impedance is the ratio of the phasor voltage all over the phasor current. So in other words, like Ohm's law, okay, if V in terms of phasor is equal to current in terms of phasor multiplied by Z in terms of phasor, so impedance is simply equal to voltage phasor all over current phasor. But we know that voltage and current and impedance are already in complex entity or phasor. So it means when you say phasor, okay, you say phasor, this already discussed, I think, on the last few topics, that you have a magnitude and you have a direction part. I could say angle theta. And Z has a arrow sign or a hat. So it means a phasor, okay, has a magnitude and a direction part. It can be plus or minus angle theta. So for the meantime, okay, we will tackle this more on the next few lessons. So please just subscribe on my channel so that you can see the succeeding lessons behind this. But when you say phasor, it is a complex number that has an impedance, it has a magnitude and a direction part, okay, which is in terms of angle. Now, angle theta. Now, you can, as electrical engineering terms, you already know the rectangular and polar, right? This is a polar value, but this can be expanded more, okay, in a complex entity. It is R plus JXT. So it means the total reactive components of the circuit. But anyway, okay, we will discuss this further on complex numbers, okay, complex impedance. Okay, now that's the meaning of the impedance, but a more feasible or a more sounding definition is impedance is the total opposition to the flow of the sinusoidal current. So it means if you have a current, you have impedance, that's the total opposition. Okay? Now we have some simple, okay, a very, very useful table, just for review, and we can see, the different formulas that we can use for converting, no, from frequency domain. So resistance, if that is alone in the circuit, your total impedance is Z is equal to R. Then take note, Z here has an arrow sign, which means a phasor. Now, admittance is just the reciprocal of impedance. So it means Z is simply equal to the reciprocal, or Y, to be more exact, that's the same, is the reciprocal of your, or admittance is the reciprocal of your impedance in vector notation. So, resistive alone, yes, 1 all over R. But if you have one inductor, okay, the symbol in the circuit is like this, a sinusoid, a coil. Now, the equation is J omega L. So this J here, no, just a review, the J here is a complex number which is simply equal to 1 bar 90. Okay, we have a separate lesson about this. So again, just subscribe on my channel, then we will discuss that further on the next few lessons. So Z is equal to J omega L, and as I mentioned, no, omega, we discussed this one, no, on our previous topics, that's angular frequency. So that's why, okay, this topic is more on frequency domain. And then the reciprocal of it is simply equal to 1 over J omega L. And last but not the least, no, your capacitor, which has a symbol like this, if that is alone, okay, the equation is like this, no, 1 all over J omega C. Now, another form of this one is if 1 over J is simply equal to negative J. So you can have this one, no, as negative J 1 all over omega C. So this is the same. Okay. So 1 over C, 1 omega C is your reactance. Okay. So called this one is your capacitive reactance, XC. XC is capacitive reactance. Okay. This one, omega L, no, omega L alone, is the so-called XL, inductive reactance. XL is inductive reactance. So please don't forget those terms. We will tackle this more when we go to the problem solving. Okay, since this is just a refresher, refresher course, so I think you already know those terms. And last but not the least is if you want to get your admittance in terms of capacitor alone in the circuit, Y is equal to J omega C. Now we will tackle complex impedance on the next slide. Hello once again. Now we will tackle now the complex impedance and complex admittance. So what are the composition of in terms of polar and rectangular forms of a impedance and admittance, which is very important on circuit analysis, and if you considering when we go to the transmission line performance. Okay, as I have mentioned before, that we can have the impedance and admittance, or an impedance first, in terms of a complex quantity. So we can have the impedance in terms of R plus or minus JX, no, which is the general form. But a more general form can be done like this. So you can have this one in terms of R, okay, plus J, okay, XL minus XC, wherein this one is your X. Considering again, this XL minus XC is what? Your total reactive components. So the minus there is negative J, as we have mentioned before, for an XC, which is 1 over omega C. Okay, now let us move further to a more detailed discussion on what is complex impedance. As we have mentioned the last slide, it can be in terms of polar relationship. So we can have Z bar plus or minus angle theta, wherein Z is the magnitude of the impedance and theta is the angle. So this is like similar way on phasors and sinusoids from our last discussion. So it can be in terms of complex entity, R plus JX. And then in terms of a more technical here, this one is in terms of a Euler identity. You can call it as a Euler identity. And this complex notation, complex numbers, is being developed by Charles Steinmetz in the 1800s. So again, it opened doors to easy circuit analysis and then to polyphase. Now, what's the difference between the angle here and the angle here? This angle here is in degree. However, in terms of exponential, the Z here is still the magnitude of the complex number. But the E here is in terms of exponential plus or minus J. The theta here is in terms of what? Radian. If you're considering this form. Okay? So as you can see, you can recall our first discussion on the basic fundamental that the angle theta is simply equal to the time dependence or argument omega times t. So it can be radian, it can be degree, or etc. So rather, theta can be only radian and degree. Sorry for that. Okay, now you can also have this form in terms of cosine and sine function. So real and reactive part. So Z cosine theta Z times cosine theta plus or minus J sine theta. So, but the theta here, please take note, that is in terms of degree. Okay, since we already have the complex impedance, how about the complex admittance? Why? So this is being defined on our last slide, that 1 all over Z, or the reciprocal of the impedance, which is simply equal also to this, in terms of complex entity, G plus or minus JB. Okay, what is G? This already looks fun to you, but this is different on AC, okay? Conductance. B here is simply your susceptance, okay? In other words, okay, this will be in terms of 1 all over R plus JX. Okay, now, you have plus minus, it will depend on the value of your total susceptance here. But we can get G and B independently, okay, in terms of R and X. So how you will do that? Just rationalization. Okay, considering here in this example that you have 1 over R plus JX, which is simply equal to G and B. You can multiply this one by R minus JX, the conjugate of this. Okay. And then it will eventually, by a little bit of mathematics and equating some of the terms so that you can get G and B. Surprisingly, G is not equal to 1 all over R because you have a reactive element. So, this is the equation for conductance if you have a real and reactive component, and you have here your susceptance, which is, don't forget the negative there, negative x all over r squared plus x squared in terms of magnitudes. So we can have these two. As you can see, they have the common denominator, and then we separate entities. But take note that the G here, conductance, is not equal to 1 over R, except if you have an x is equal to 0. There's no reactive element on the circuit. And hence, you can go again to this basic equation from our DC network theorems that, or DC circuit, that G is simply equal to the reciprocal of resistance. So since we are on frequency domain, so reactive components is also involved. Okay, we will go to series and parallel RLC circuits.